Hey everyone, so today we're going to be looking at correlation matrices in Python. I'm just going to show you a very simple example first, and then if you want to stick around for some interpretation and something a little more complicated using market data, that's what will be coming up. So I'm going to be using my favorite package as usual, Pandas. So I'm going to import that, and then I'm just going to create a couple vectors of related data because that's what correlation matrices are all about. It's about determining relationships between data columns. So you can see these two are exactly the same, and then I'm going to make one data column that is the exact opposite. Now I'm going to create an empty data frame. This is using Pandas, PD. And then I'm just going to start putting in these three data columns. So dfx equals x, df y, oops, equals y. Man, sorry, I'm bad at typing. And then let's just, okay, so now if I type in df, you can see I've got all of my data in there. And then all that's left to do is this is Pandas function for correlation matrices, core, and then just open parentheses. And so here are the correlation coefficients. And so the way to look at this is that correlation coefficients are always numbers between 1 and -1 inclusive, and they're 1 if the data is positively correlated exactly, and -1 if it's negatively correlated exactly. And so you can see z is negatively correlated to x and y, and then positively correlated to itself, and hopefully you can interpret the other two data columns. And let's just, for good measure, add in one that is just completely unrelated. And let's do it once more. So you can see W is not really too related to these other data columns. So that's why it's not getting a value of 1 or -1. It's getting something in between. Okay, so now that we've done that, let's look at something a little more complicated. Over here on the left, I have a portfolio optimization program. This is just my file for getting the live data. I have another video if you want to check how to do that out, but here's the file, or the function right here. It uses yfinance. Okay, but we're talking about correlation matrices, and this is the function that does that. So I'm going to call that and type in some securities. So let's put in the S&P, some long-term treasuries, and then just some of the usual suspects. Okay, and we'll do it this year up until today's date, which is the 19th. Okay, so you can see these are all positively correlated. I kind of thought maybe treasuries would be a little negatively correlated, but let's just have a look at this. So you can see along the diagonal we have a 1 because, of course, they are all exactly positively correlated to themselves. And you can see Apple and Microsoft, they're both pretty positively correlated to the S&P, not as much correlated to treasuries. That totally makes sense. And they're also positively correlated to each other even more than the S&P. So the way to read this is Microsoft has this correlation coefficient in relation to Apple. And that makes sense because they're both tech stocks, both highly correlated. And a way to think about this is if you had both of these, both Apple and Microsoft, in your portfolio, they would exhibit similar returns, and so you wouldn't want to invest all of your money in both of them because they're positively correlated, and so if one goes down, they're probably both going to go down. And that's why you look for sometimes negatively correlated securities so that you can balance your portfolio. So on this channel, we don't just put in the code and that's that. We also like to look at the math behind it. So this is the formula for a correlation coefficient, where R is that coefficient. And so X and Y you can think of as two data columns. For example, here X and Y. So the way that this works is X bar and Y bar are the averages of the entire data column, and then Xi and Yi are individual data points in those columns. So the program first calculates the average of the total column, and then it sums up, this is the summation notation, it sums up the difference of each data point from the average, and then it does that for both the two columns and then multiplies them against each other. Now let's look at an example real quick. So here we've got our X and Y data columns. The average, hopefully you can recognize it as being 2. And so if we were to subtract 3 from 2 and 3 from 2 for the third data entry, we would get 1 times 1. And then in the denominator, it does the exact same thing, but it squares those differences. And so we would get 1 times 1 over 1 squared times 1 squared. And that, of course, gives us 1. And it does that for all of these. And the same exact, we would have the same exact effect here. 1 minus 2 is negative 1. 1 minus 2 is negative 1. Negative 1 times negative 1 is positive 1. And then the same thing in the denominator. And that's why the correlation coefficient between X and Y, if we look here, X and then Y is 1, or alternatively Y and then X, okay? Or here Y and then X, 1. And then if we look at the Z versus Y column, we see, in this case, let X be Y and let Y be Z. If that's just confusing, and perhaps that made it more confusing than it needed to be, just we're talking about the Y and Z columns here. So the average of both is still 2, except because we've switched it, in the numerator, it's going to be 3 minus 2, and then 1 minus 2, so that's going to give us a negative 1 in the numerator and a positive 1 in the denominator, and that gives us a negative 1 correlation coefficient.